Okay, so the next speaker, final speaker, is Chethan Gowdigere from ISR Bhubaneswar, and he'll be telling us about classifying three-character rational CFTs. Okay, Chethan.
Can you hear me?
Yeah.
Okay. So first, let me start by thanking the organizers for giving me this opportunity, and also thanking Alok and his team for all the hard work that has gone into this conference. So the title of my talk is Classification of Three-Character Rational Conformal Field Theories. So it is based on these two papers which have fortunately been published in JHEP. And I should point out my collaborators here. All of them are PhD students. Arpit Das is a PhD student in Durham University. Jagannath Santara is a PhD student in NICER, where I work. And Jagannath is actually graduating soon, and he will be soon applying for postdocs. And Sachin is a beginning graduate student. Okay, so a classification scheme for rational conformal field theories is known as the MMS program. It's named after Mathur, Mukhi, and Sen, the founding fathers of this program. This program was set up more than 30 years ago, and I believe at least two of the founding fathers are participants in this conference also. So though the program was founded more than 30 years ago, it lay dormant for a long time, and it was revitalized around 2015, about 5-6 years ago, by one of the founders, Sunil Mukhi. So the series of papers he wrote with his students and Gowdigere have contributed very heavily to this program. And besides Sunil Mukhi and his collaborators, other groups have contributed to this study. It includes Harvey and collaborators. It also includes the Kias group. The Kias group, I've written two important papers which I found very useful. It also includes Perlmutter, Kaidi, Lin, Para Martinez, a couple of papers, recent papers from that group. And there have been a lot of mathematics groups from mathematics departments and mathematicians who also study this problem, study the problem here for their own purposes. And I'm highlighting one such paper which will come up in this talk later.
Can I make a comment?
Sure.
Yeah, I think Gannon's results are much more general than Frank and Frank and Mason.
Please repeat.
There are some Frank and Mason's work. There are some limitations, and probably you should look at Gannon's work.
Oh, Gannon's, yes.
Yeah.
Thank you very much. Thank you. Yeah, thank you. Yeah, Gannon's work. I will look at it. I have looked at it, but not enough. I will.
Yeah, they force the exponents to be between 0 and 1. That's
I
put in mind, which is not necessary.
Okay. Anyway, so in the MMS program, the program identifies the rational conformal field theory by two non-negative integers. What is usually referred to as n and l. What is n? N is very simple. If the partition function of a rational conformal field theory takes the form of a finite sum of products of holomorphic and anti-holomorphic factors, and n is simply this number of these independent factors. So these independent factors are known as characters, and n is simply that thing. Now, n is clearly a positive integer. In this talk, we'll mostly look at n equal to 2 and n equal to 3. And n is also, n being the number of independent characters could be different from the number of primary fields. We'll see examples as we go along. N is easy. The question is, what is L? L, for a long time, didn't have any name, and recently it was named the Wronskian index by, again, Sunil Mukhi. So let me try to explain what is the Wronskian index. For that, let us recall the Q-series expansions of the characters of rational conformal field theory. So here I've given you chi-naught of Ti, which is the identity character, and the other non-identity characters is in the second line here. And the leading behaviors are also known as the indices. So the index of the identity character is minus c by 24, and the indices of the other ones are h minus c by 24. So the important thing is that these characters, they are solutions to a modular linear differential equation, which I'm sure has come up in various talks. At least I could see that it came up in the previous talk. So these are differential equations in the tau space, where the derivative is something slightly special. It's called the Serre-Ramanujan derivative. It's given here Basically, the important thing to remember is that the Serra-Ramanujan derivative takes a modular form and returns a modular form again with weight 2 times more than that. Now let's get back to the differential equation. The coefficient functions of a modular linear differential equation, just like ordinary differential equations on the whole complex plane, can be written in terms of Wronskians. Okay, and now let's recall what's a Wronskian. Wronskian is a determinant of matrices where the derivatives of the solutions are there. And the usual Wronskian is the one where the nth derivative is missing, but there are all these other Wronskians also. So the Wronskian of the characters of a rational conformal field theory is what one focuses on, and we can show you that it's modular with weight n into n minus 1, and here so there's a valence formula for modular objects. So when we apply the valence formula to the modular object, you get the formula like this. So here on the right hand side, the first term basically encodes the behavior of the characters on the Wronskian at infinity, and the second term encodes the zeros of the Wronskian. So L is the Wronskian index. L by 6 encodes the zeros of the Wronskian. Something is missing. You can't see any picture here, right?
No.
Okay. Okay, there's something wrong. Okay, basically this picture here was supposed to be the well-known, everybody knows this, the upper half plane with the SL2Z fundamental region showing. So basically we know there are cusps at the omega, the cube root of unity, and the square root of -1, there's a cusp there, and there's also a cusp at infinity. So basically, the Wronskian index of a rational conformal field theory contains information about the zeros of the Wronskian, which can either be at the finite cusps or in the interior or on the boundary away from the cusp. So a simple zero at omega gives a contribution of 2 to the Wronskian index. A simple zero at I gives a contribution of 3 to the Wronskian index. And similarly, anywhere else, it gives a contribution of 6 to the Wronskian index. So these two objects are the things that the MMS classification program identifies a RCFT by. Okay, so these two little somewhat different kind of a data is set up as an identifier for the RCFT in this classification program. So now that we know what is the important parameters, what are the important properties of a RCFT which goes into the classification program, one asks the question: well-known RCFTs, what are their NL values? So I start by discussing the very well-known Verisaro minimal models, and you can it's very well known. We know the central charge. We know the models are identified by 2 co-prime integers, and we know the scaling dimensions. So this is one example where the number of primary fields is also a number of characters. And if you put everything together with a little bit of high school algebra, we can show that the Verisaro minimal models have a vanishing Wronskian index. And this was, of course, very well known even 30 years ago. It appears in one of the foundational papers already. Now you can also ask the question, other CFTs like super Verisaro minimal models. So here I'm considering just a unitary series, which is labeled by an integer m bigger than 3. The central charge is given here, and the superconformal primaries are also given in this formula here. So we just here need to ask the question: how do superconformal primaries split under the subgroup, under the conformal subgroup, so subalgebra rather? And for the Neveu-Schwarz fields, these are the branching rules which we can read from some old papers. And similarly for the Ramond fields, there is a branching rule again. So one can do a little bit of algebra and compute the characters. And this time we find the Wronskian index is actually mostly non-vanishing, except for m equal to 3, which is also the tricritical Ising model, which is also part of the Verisaro series. That's the only one which has a vanishing Wronskian index. Everything else has a non-vanishing Wronskian index. Another class of rational conformal field theories, which one would like to know what their NL values are, is Weismuller-Witten CFTs. And all of us know that the Weismuller-Witten CFTs are parameterized by a simple finite algebra and a level K. And the formulas for the central charge is given here, very famous. And the Weismuller-Witten primaries are obtained, the number of Weismuller-Witten primaries of the theory are obtained by solving, finding non-negative integer solutions to an equation such as this, which involves the level. And every Weisel-Levitin primary carries a representation of the finite simple Lie algebra. And using the data of the finite simple Lie algebra, which is we can compute the scaling dimensions. Now, in this problem, the number of characters and the number of solutions, the number of characters and the number of primary fields are usually different, not always same. Okay, this is because of some symmetries in the Dynkin diagram. Again, there's a big blank space here and something wrong with my setup here. The diagrams which I wrote by hand are not showing up. So basically, the diagram shows the Dynkin diagrams of D4 and DR and AR and E6. So these are diagrams which have a symmetry, and in all these CFTs, the number of primaries are not equal to the number of characters. You have to study solutions to this equation modulo the symmetries of the Dynkin diagram. And this is not the main part of my talk, but we wrote a paper where we studied all these CFTs and identified them according to the MMS identifiers. So some results are displayed here. One thing is that SU2 Weisel model at all levels have a vanishing Wronskian index. And we also show that all the algebras at level 1 have a vanishing Wronskian index. And we also found exact formulas for Lie algebras at level 2, and there you find that the Wronskian index doesn't vanish except for small ranks. And there are some surprising results like A2 at any level and G2 at the same level have the same N and L values. Okay, so let's go on with the main problem of MMS program, which is classifying RCFTs. So the main point is the following, that for any given NL, give me an NL value, there's a unique MLDE up to some constant parameters associated with it. And the main point here is that all RCFTs with the same NL values solve this MLDE. So all NL RCFTs solve one single MLDE, of course, for different values of the parameters of the MLDE. So I want to illustrate this very nice principle by examples only. The main thing is to remember that the coefficient functions of the MLDE are related to the Wronskians of the solutions. So for example, when the Wronskian index is 0, the Wronskian has no zeros, and hence all the coefficient functions have no poles and are holomorphic, and we can just use we can quickly construct the MLDEs. Okay, so I've given you shown you 3 examples here, and I've adopted a small notation here. The parameters of the MLDEs, I've written it as mu AB. That's the parameter which accompanies the term E4 power A and E6 power B. So a 2.0 MLDE has 1 parameter, a 3.0 MLDE has 2 parameters, 4.0 MLDE has 3 parameters, etc. So similarly, I'll give you one more example for n at comma 2 MLDEs. So the Wronskian is a 0 at the cube root of unity, and hence it can have a pole there. Is a question there?
Yes, sorry, Chethan, sorry to disturb. One question. So when you calculate N and L, you calculate them from Virasoro characters or characters of whatever chiral algebra is at work? For example, for the Kac-Moody, for the WZW models, do you use the Kac-Moody group, or maybe you said that and I missed?
No, I use the Virasoro characters. I'm counting the Virasoro primaries.
No, you're not counting the Virasoro primaries. As you said, the partition function is a sum of mod squares, right? Of terms, and that's a finite set of terms. So you're using those. So those are not all the Virasoro primaries.
I see. So the characters under the biggest chiral algebra is.
That's correct. But we don't even have to know what is the chiral algebra. We just we just specify the number of characters in advance, right? So in principle, one doesn't even know what the chiral algebra is at that stage.
Okay.
The N of Chethan defined N and L. So that N is the number of characters under some generalized chiral algebra, what the biggest one, as you said.
I see.
But one doesn't know what it is. But it's not the Virasoro characters, huh, Chethan? Presume-Innovitin models have infinitely many Virasoro characters, but you're not summing over those.
Yeah, but linearly independent characters is what.
No, but they're not Virasoro characters. Virasoro characters by definition are just characters of the Virasoro algebra only.
Yeah. Sorry. Yes.
Yeah, I think that is just terminology, but I think it's
okay. I see. And then the chiral algebra could be a label in addition to N and L, right? In the
no, I think that's an output of this procedure. So it's not a label.
Okay, thank you.
Okay, so let me continue. So the point here is that given an N and L, you can construct an MLDE and you are meant to solve that MLDE to find all CFTs with that particular N and L. So this was implemented early on for 2.0 and 2.0 MLDEs and 2.0 CFTs in the original Mathur paper, MMS papers, and also for 2.2 MLDEs and 2.2 CFTs starting from that time and completed more recently. So I want to start solving MLDEs. So basically the story is quite simple. We just use Frobenius method and we call something as admissible character solutions where your characters are, where you impose that the identity character Fourier coefficients are positive integers and the non-identity character Fourier coefficients are positive rationals, but then they can be made positive integers by multiplying with a common denominator. So this is the point here. One has to scan the space of parameters of a MLDE and look for admissible character solutions. So more parameters there are on the MLDE, the problem becomes technically harder. Okay, so now the one parameter MLDEs are the 2.0 and 2.2 MLDEs, which was studied long back, and two parameter MLDEs are 3.0 and 3.2, which I will talk about in the rest of the talk. And three parameter MLDEs are 3.3, 3.4, 4.0, which I'll probably come in the future work coming up in that direction. So we start with 3.0 CFTs. So here we have two parameters in the MLDE. So the strategy we follow to solve this thing is that we take two equations. One is the leading order equations from the Frobenius solution and the next to leading order equations from the Frobenius solution. And we evaluate both these equations for the identity character and solve the two parameters in terms of identity character objects such as alpha naught and M1. So that's the main point here. We exchange quickly the parameters for identity character objects. And then we go to the next Fourier coefficient, that's the M2. And this is this big equation, which is written in small print. The main point here is that all these equations are there in the original MMS papers itself. The main point here is that this is an equation where everything is an integer. Okay, everything is an integer. So we can conclude that n needs to be an integer by the integral root theorem here, because there's an equation for n and all coefficients of that equation are integers. So we use the integral root theorem to conclude that n is an integer. And so what this means is that the central charge, which can be written as n by 70, and this is where our computations become simpler. What it's telling us is that the central charge is always an integer divided by 70. So if I want to study CFTs in a range of 1, say, I only need to do 70 computations now. Earlier I had to do a lot more computations. So this is what I do.
Sorry, I'm confused about something. If I have a polynomial equation whose coefficients are integer, doesn't mean the solution is integer, right?
No, the coefficient of n power 4, the leading power is also 1.
Yeah, but I can have a quadratic equation in x squared plus ax plus b equals 0. That certainly doesn't have integer solutions for all integer a and b.
If this equation admits a rational root.
If it's rational, then it's integer. Okay,
yeah,
that I can.
CFT. Yeah.
Okay. If it's rational, then it will be integer. Yes.
Yeah. So this is actually this equation is from your old paper, and this conclusion is also from your old paper. Very nice conclusion. We just managed to take that conclusion and say that now our central charge will always look like an integer by 70. Okay, so if I want to study, look for CFTs between 0 and 1, I just need to do 70 computations now. So this is just what we did, and we get 2 Diophantine equations for 4 variables, and we just have to solve one by one. And this is just what we did. We studied up to C less than 96. We had to do 6,720 computations, and we found many admissible character solutions. There were 303 discrete solutions and 2 infinite series. And I want to try to, I just put some tables from our papers just to show that these solutions are there, a lot of them. So the first row indicates the solutions to the two Diophantine equations, and the first four columns, and the other columns indicate other data of the CFT, which was the potential CFTs, which was derived. So we organized all these solutions into 5 categories of solutions. I'll only talk about 4 of them. The first category is simply well-known RCFTs, which are being rediscovered here, so I won't spend more time on them. And then there's a third category of solutions, which we call the third category. So these are Frank Mason vertex operator algebra solutions, which is being rediscovered here by us. But these solutions already existed in the literature. But these are still at the level of admissible characters, and we still don't know whether they will give any potentially new CFTs. And the fourth category of solutions is what is known as the GHM dual. So GHM, Gabeldiel, Hampapura, and Mukhi showed us how to construct new CFTs starting from a metamorphic CFT and an affine subtheory. And we refer to these as denominator theories and coset theories, or duals, GHM duals. And there is a situation where both the coset and the denominator are 3-0 CFTs. And in such a situation, the central charges have to add to 24, and the scaling dimensions have to add to 2. So what we found is that there are 15 of the solutions that we found are actually just GHM duals of known solutions. And many of these, many or probably all, are constructed or anticipated by GHM in their paper. They're just being rediscovered here. And the last category of solutions, so we just have 7 solutions. The fifth category, 7 solutions. And here we actually found some solutions which seems to us to be new. And JHEP also agreed that it is probably new. So we have, after finding so many solutions, there are only 7 of them which are really potentially new admissible character solutions. So I have just written down the characters of these 7 solutions just to show that we actually got it. And I have to mention here that this 3-0 CFT work was done by us, but it was also done by 2 other groups. And you can see the archive numbers here. We were within the space of 4-5 days, we put our papers unknown to each other. At least I didn't know any of that they were working on this work. So 3 groups kind of discovered the same kind of results using very different methods, actually.
Chethan, can those characters be written in terms of hypergeometrics?
Yes, they can be, actually, but
they're all hypergeometric type.
Yeah. There's a way to go to that lambda. That lambda is that gamma naught. Yeah, so there is you can go
in terms of J, you have to use a J function and write.
J. We can do it with J, and we can also do it with the Hopf module of some other gamma naught 2 or something.
Yeah, okay.
That's
right. I mean, that's the analog of J.
Yeah. Okay, so that was 3-0.
5 minutes.
Yeah, so that was 3-0 CFTs, and 3-2 CFTs. The technical content is similar. It's also a 2-parameter MLDE. So we follow the same procedure, hoping to find new CFTs. So I won't repeat the procedure. It is just that this time the problem is a little more harder. The central charge is an integer divided by 210. Okay, so if I want to search for CFTs in a central charge range of 1, I will need to I will need to do 210 computations. And we did do this 210 computations for every central charge 1 range for up to C less than 96. And we managed to find only 9 solutions, only 9 admissible character solutions. And these solutions are not very satisfying because they are just the 2-0 CFTs which were discovered by MMS 30 years ago. Those solutions adjoined with a constant character. A constant character is a solution where the Q series is just the number 1. Okay, so the scaling dimension is exactly C by 24, so that the index is 0 and all Fourier coefficients vanish. So such trivial solutions, well, in some sense they're trivial because you don't get probably a new CFT. You have an old CFT adjoined with a constant character. So we just get back those solutions. We just get some old solutions in some new bottles. So the next question one can ask is, okay, now we have admissible characters. How do we get to CFTs? And this is also something in the papers of when the program was established 30 years ago. Beautiful papers were written and whole procedures were set up how to go about this story. And since I'm not doing too well in time, I will probably not spend too much time on it. So I'll just say that one can ask the question. One can go to the one can go from the tau plane to the lambda plane, where lambda is this object associated with the Hopf function of some particular congruent subgroup. And then you have a hypergeometric function, hypergeometric differential equation. And there we can compute how the S transformation of the SL2Z acts on the character. There it acts as the monodromy matrix of the solutions of the differential equation. And once we know S, we can do many things with it. For example, we can ask the question, we can compute the number of primary fields associated to the characters. And so we did this for, this is work in progress, and it is still, many doubts are there, many questions are there. But we seem to get these theories where the number of primary fields are really large numbers like this. And yeah, there is more work to be done here. And this is just a direction of what is happening in this work. And there are some more results that's coming out of this tree classification is that we found many pairs of CFTs which are potentially GHM dual pairs. That means they have central charges which add up to 24 and scaling dimensions, which conformal dimensions which add up to 2. And among these pairs, some of them are pairs of well-known CFTs, and some of them are two unknown things, but they seem to be dual to each other. They seem to be dual to each other. So these are also questions which can, these lead to many questions. Is there what is the meromorphic CFT that is underlying this suggested GHM duality? Yeah, so this is the upcoming work. So we hope to make progress in solving 3-parameter MLDs along the techniques established for 2-parameter MLDs in this talk. And also explore more aspects about the GHM duality which we are observing within the 3.0 classified RCFTs. Okay, I will end my talk here. Thank you very much for your attention.
Thank you, Chethan. Any questions?
Yeah, can I ask the question?
Yeah.
Chethan, how do you determine the S matrix? I mean, T matrix you get from H. That's very easy. But how do you get the S for any of these characters?
S matrix is a, well, let me try to, I'll try to say it in, so the way the S matrix S acts on lambda is it acts on lambda in a certain way. I think it's lambda by 1 minus lambda or something. And you just you just write the solutions of the differential equation in terms of hypergeometric functions.
Okay.
And then you just impose, you just ask the question, what happens to this character when lambda goes to that? And then, yeah, that's how you do this procedure. I'm speaking very stupidly, but that's mostly kind of the thing that's going on.
Yeah, I had a couple of questions.
Yes,
so,
sure.
And a comment. So one comment is I think Suresh asked if these are hypergeometric, but I'm pretty sure these these solutions of this are not hypergeometric functions, right? Because these are sets of 3 functions that go into each other under monodromy. And my understanding was that hypergeometric are you have 2 functions, you don't have 3.
No, Ashok, not Ashok, sorry. Sunil, rank 3, you have, I mean, all the Frank Mason rank 3 things are hypergeometrics.
Okay, I mean, in 1989, there was a paper by myself with Sudhakar Panda and Ashok Sen, in which we showed that this general equation has a solution in terms of contour integrals. Now, it might be that those contour integrals are some rank 3 hypergeometric functions, but just to add to what Chethan said, you know, that those contour integral representations are enough to calculate the Sij. And
cool.
a year ago, I wrote a paper with Palash Singh and Rahul Poddar called something like contour integrals and modular S matrix. So that does a much more general class of cases.
Oh, Very nice.
So that's one thing. The second comment I had was, can you go back, Chethan, to that case where you have a list of your 7 exotic theories and you found some very large number of primary? Yeah, no, not this. Very large number of primaries. You had a table.
Yeah. Just about
Somewhere near the, this.
Yes.
Now, in this list, you don't have central charge 8 and 16. Is that right?
Yeah, no, these are the new ones which there's no 8 and 16.
But 8 and 16 were found actually, in fact, they were found first by Hampapura and myself, but we didn't understand what they were. And then the Korean group discovered them again. And I was working with them. We were able to show that those also have very large degeneracies, like these kind of 6 or 10 digit numbers in the partition function. And it's a very interesting open problem to find out what CFTs these are, because they obviously have some number theoretic significance because of these very large degeneracies.
Yes.
Have you tried putting these numbers on OEIS?
Yeah, I don't know. Yeah, I have tried a few things with the numbers, but yeah, maybe
put them on OEIS and see if they show up somewhere.
Yeah. Okay, thanks.
Okay, thank you.
Okay, any other questions? Okay, then thank you, Chethan. I think it's